welcome back, Mindsetters. As you already know, we are doing trigonometry, and the show has been absolutely amazing because most of you guys have managed to join us on this lovely spring Monday, and I hope that your weekend as well, Saturday, was Spring Day, the 1st of September. So I hope that you guys had an amazing spring because it's just so warm and lovely in the studio as well. It's nice and warm, so I'd really like you guys to ask us questions right about now because it's so warm. There's no excuse not to. So in case you're not understanding or there was a question in your exam that you didn't understand on trigonometry, please don't fear asking us right now because this is what we are here for. Over to you, Dina.
Thanks very much, Katlego. And yes, grade 10s, we've found the calculator. So let's get back to that question that we were on. We were trying to find the angle A, where cos A equals 2 over 6,457. And I'm sure in the break some of you would have worked out what that angle is. So let's see what my calculator shows me. 71,956. So I would round off to just 72,0 as an angle. So that would be 72 comma 0 degrees. So that's that angle there. Okay, so let's just fix it up here. There we go. And let's just go down here. There we go. Angle A is 72. Remember, angles got little cuppies and degree, and the values have got degrees on them. Okay, so that was solving for the angle. Now, what was the question that somebody posted around isolate? They wanted to know, I've used the word isolate. What does that mean? That's just a fancy way of saying, if I've got 4x minus 1 equals 5, I will say to you, solve for x. So solve for x means 4x equals 6 and x equals 6 quarters. Okay. Now I'm using sort of layman's terms and saying isolate the x. So when you are placed in isolation, it's only you and yourself. There's nothing else around you. So currently the x has got a -1 added onto it. Actually, the x has got a 4 that's being multiplied by it. It's got a -1. It equals 5. So when I'm solving for x, I'm actually isolating the x. I'm making it by itself. Now, I'm using the same terminology in trig because when I say solve for x in algebra, it's quite an easy way to say isolate the x. But in trig, it's a lot more complicated to say solve for tan A because you really are solving for the angle, but you're solving for tan A at the same time. And in solving for the angle, there's a couple of processes that must happen. And so one of them is to try and get that ratio by itself. So instead of me saying solve for tan A, which is quite a complex thing, or solve for sine A, or solve for cos A, I'm saying isolate the trig ratio. Make sure that the trig ratio doesn't have coefficients. Make sure that it doesn't have terms attached to it. Then you've isolated. Then you can solve for the angle. I hope that makes sense. So isolating x means x has got a coefficient of 1, it's got a denominator of 1, it's standing by itself. And that's what we're talking about when we're dealing with the trig ratios. Okay, so that was a question on isolation. So let's see what's here. Right, let's see what's there. Okay, so let's go on to 4. There we go. Right, now we're going to change direction slightly. Okay, that's not what I wanted. There we go. That's better. Okay. I'm going to give you a trig equation. And the reason I'm saying we change direction is because I'm actually making this angle an angle that is larger than 90 degrees. And remember earlier somebody asked the question, is a triangle always 90 degrees? For this kind of trig that you're working with SOHCAHTOA, yes. But we can get contexts where angles are larger than 90 degrees. And then what are we going to utilize to help us in formulating the theory that is going to help us to solve for those various ratios? So when that happens, we are going to use the Cartesian plane. And we're going to do two things. Firstly, we're going to have that the way that we measure angles is in anti-clockwise direction. So we're going to have what we call quadrant angles, which is when we rotate to 90. Then if we rotate to 180 and rotate to 270 and rotate to 360, we will rotate in the anti-clockwise direction. And then this theta that we are measuring here is said to be in standard position if, I think I'm actually going to find another page here and just do that. Okay, let's do a little bit of theory on the side here and we'll come back to the question. So measure anti-clockwise. And then the second little bit of terminology is that theta will be in standard position from 0 degrees, so it will be rotated in an anti-clockwise direction. And where it stops on the Cartesian plane, it will have coordinates x, y. Okay, now if this arm here had to travel to a new position, what is the path that this theta would, or this ray would follow into the next quadrant? And this blue theta is bigger, so we're going to call him beta. And then we're going to continue rotating into this quadrant. So we've got this angle at this stage, and this angle is larger than 180 degrees. Can you see the path? What is the path that's forming? So it keeps going, path, all the way into this quadrant, and all the way back there. So I think you can clearly see that this angle that it stopped there would be all the way there. Okay, so theta was acute, then it became obtuse, to the pink one which is reflex, to the green one which is bigger than 270 degrees. So we are going to utilize this rotation of this ray to help us with the connection between the coordinates of the ray and the size of the angle. And what we call the path that this ray has taken to create all these angles that have become bigger and bigger is obviously the circle. And the circle has got a relationship. A circle is not a function, but it is a relationship that looks like this. The abscissa squared and the ordinate squared will give you the radius squared. Okay? So we've got, at any of these positions, take x squared and y squared and you'll get the length of the radius. Now what is the length of the radius? Well, it's the length of this segment that's in standard position. So that would be the radius. That would be the radius of the circle. That would be the radius. That would be the radius. They're all radii. Okay? So the relationship between each point and the radius is formulated by that equation. So in each of those quadrants, we're going to find that in the first quadrant, since the angle's acute, theta's acute, and the quadrants work in exactly the same way as you've worked with them in algebra, so it's quadrant 1, 2, 3, 4, we would say that every single ratio that you work out would be positive. However, when you get to the second quadrant, let's look at sine of 120. That's positive. Let's look at the cos of 120. That's negative. Let's look at the tan of 120. That's negative. So obtuse angles have got this interesting relationship. Only the sine of obtuse angles will be positive, but cos and tan will be negative. So we're going to say that in here, we're only going to capture the ratios that are positive. What happens to the pink angles? Well, let's go back to the calculator. What happens to something like sine of, let's make it 210. What do we get? Oh, that's too big, 2210. Let's just correct that. Sine of 210. That would give me negative. What about cos? Cos of 210. That would be negative. What about tan of 210? That would be positive. Interesting. Tan is positive, but sine and cos is negative. So, tan would be positive in this quadrant. And what happens in the fourth quadrant would be a green angle, so an angle that's larger than 270. So let's take the, let's say cos of 330 bigger than 270. That's positive. What about sine? 330. That's negative. And what about tan? That's also negative. So as you saw, only the cos is positive, but all the other ratios will be negative. So what we've captured over here is that in each of these quadrants, these are the positive ratios. All the other ones will be negative, the ones that we haven't captured on this diagram. And if you read this word, it says C-A-S-T, cost. So we call this the cost rule because it will be a rule that will govern every single ratio that we'll be working with. So knowing that information, we're now going to take that and we're going to put it onto this information over here. Okay, which was to say that if we are given that information and that information, we must draw a diagram with theta in standard position. Well, we first need to know, is it a theta that's going to be in the first quadrant, second quadrant, third quadrant, fourth quadrant, and this information is going to be able to tell us. So let's work with the information first. If we have 5 tan, let's isolate the tan ratio. So we've got tan theta is equal to negative 2 root 6. So tan theta is therefore negative 2 root 6 over 5. Can you see that I've now got a negative ratio? And our cost rule, which we're just going to put over here, says that it's only in quadrant 3 that we've got a positive tan ratio. But in those two quadrants, 2 and 4, tan is negative. So I'm just going to capture the information in the two quadrants with a little tick. So we could have tan in there, or we could have tan in there. And the next little bit of information is that the angle must also be between 0 and 270. So this quadrant here, quadrant 2, shows us that both of these restrictions, the tan is negative and the restriction on the angle, will actually happen in quadrant 2. So to draw the diagram that they require would mean us taking a quadrant, drawing in the angle, so it's rotating from 0 degrees all the way to quadrant 2. We would then fill in the radius and say that this is the angle we're referring to. But the one thing that we haven't discussed is, how does this ratio impact on this picture since it's not 90 degrees? Okay, well, for that we actually have to go back to the theory board. So let's go back here and just give you a little bit more of definitions. And that would be that for any angle that's larger in the Cartesian plane, we define the ratios in a slightly different way. So we've got coordinates as opposed to opposites and adjacents. So we'd have y over x. So these are the definitions for each of those three ratios. I'm only going to go with those three. The reciprocals will work in exactly the same way. And for this acronym, we often say, well, some people have used, not we often say, but it's good to just put the capital letter C, X, R, and T, Y, X. And something quite funny is to say, how do I remember this if it's for the Cartesian plane? And that is shield your rear, cause X rays tan your exterior. So that will be quite funny to remember that. But this is the Cartesian planes version, as opposed to the version that we started the lesson with, which would only apply to right angle triangles. Okay, so let's go back to the diagram that we were busy with. And we've now got that the definition of tan on the Cartesian plane, shield your rear cos x raised tan your exterior, is y over x, right? So in this quadrant, it would mean that the y value, it is positive, and the x value is negative. So my negative would have to accompany the denominator, and that will be negative 2 root 6. Again, the context governs us. Any x's are negative, and the y's are positive. Okay. Now, if I say a negative divided by a positive, I'm still getting a negative ratio, or a negative divided by a positive, I'm still getting a negative ratio. So when you convert back into the Cartesian plane, be very careful about the signs that you are using. So standard position then means that we have the radius and an x value and a y value, and we've got the size of the angle. So standard position is really in which quadrant will that angle lie in. Okay, now to end off, we will look at, with the aid of the diagram that we've just drawn and without using the calculator, okay, evaluate what 14 cos theta plus 7 root 6 sine theta would look like. Well, 14, the definition of cos theta would be x over r plus 7 root 6, and that would be y over r. So we could now substitute in, and we'd get 14. The x value you saw was minus 5. We then have to work out what our r is. 7 root 6. Y was, let's just go here. We haven't yet worked out what our r is. So we would get x squared plus y squared would be equal to r squared. So x would be 5, and y is 2 root 6 squared is equal to r squared. So we would get 25 plus 4 times 6, which would be equal to r squared. So it's 24 and 25, which is 49. So therefore r would be 7 in this context. So we get a 7. And then it's 2 root 6. So let's go on to our next page. And this r is 7. We've worked it out now. And this y was 2 root 6 over 7. Okay.
Dina?
So, yes.
Our time is running
okay.
out. But you can carry on with
Okay,
that.
I'll
just to
finish
it
that.
off.
So that's negative 10. And that's 7, 7. So that would be 2 times 6 is 12 plus 12. So we get 2. So that's just working with angles that are bigger than 90. We'll do a lot more of that in grade 11 as well. Thank you.
Thank you, Dina. Guys, as we know, it always goes so super fast when we're having fun here at Mindset. I think that they should start making the hours like 2 hours or 3 hours, just so that we have enough time to cover everything. Thank you guys for such an awesome show. You guys were absolutely amazing. Remember to keep learning extra and learning more. Thank you again to Liberty. It has been an absolutely fantastic, spectacular show. See us next for grade 11s if you want to join us. Bye, guys.